initially the particle is here. So t equals 0, the particle is here. Now, since the particle is moving at uniform or constant speed, its angular speed is constant. That means the angle that's swept out every second is constant. Let's call it omega. So in t seconds, the angle swept out will be omega times t. So in 1 second, the angle swept out will be omega. In 2 seconds, it will be omega times 2, and so on. After t seconds, it will be omega times t. So here's the position vector. Let's write position vector r in terms of I and j basis vectors. Well, I is pointing in the positive x direction. The side adjacent to omega t here is the magnitude of this vector, or the hypotenuse of this triangle, which is r without a line underneath it, times the cos of omega t. And the side opposite omega t is r sine omega t. So vector r can be written as r cos omega t times unit vector I, that's pointing in the positive x direction, and onto that we add on this vector here, r sine omega t times j. So we're just using the triangle law. We're just adding this vector onto this vector here by the triangle law. Now let's get the velocity vector. So we saw in the previous video that the velocity vector is the derivative of the position vector with respect to time, and we saw that we can do that by differentiating each of the components with respect to time. Now r is just a constant here. That's just the magnitude of the position vector. That never changes because we have a circle here. So we differentiate the cos function to get minus sine, and we differentiate the angle to get omega. So both r and omega are constants. When you differentiate the sine function, we get cos, and when you differentiate the angle, we get omega. So here we'll get r omega cos omega t times j. So that's the velocity vector. Now, in which direction is the velocity vector pointing? Now, it turns out that the velocity vector is perpendicular to the position vector for an object undergoing uniform circular motion. Now, to show that, we can get the dot product of the two vectors. To get the dot product, we multiply the I components together. So we're going to get minus r squared omega times cos omega t times sine omega t. Just multiply the I components. Then we multiply the j components together. So we have r squared omega sine omega t times cos omega t. And we can see that we get 0. So we get a scalar, of course, and that scalar is 0. So what does that tell us about the vectors? Well, if the dot product is 0, it means that vector r is perpendicular to vector v, and that's something you might expect. So this is vector v. So this vector is on the tangent that touches the circle at the particle, because we know that for a circle, the tangent is perpendicular to the radius line from the center to the point of contact of the tangent. Now let's get the speed of the particle. Well, the speed is just the magnitude of the velocity. We could show it like that. That's the length of the velocity vector. We could also show it as v without a line underneath, or an arrow overhead. So we want the magnitude of this vector, so we just use Pythagoras' theorem. We get the square root of the sum of the squares of the components. So we square this component. Well, that's going to give us r squared omega squared sine squared omega t. Then we square the other component. That's going to give us r squared omega squared cos squared omega t. Now we can factorize out the r squared omega squared. And then we're left with sine squared omega t plus cos squared omega t. Well, that's just 1. So the square root of r squared omega squared, that's just r omega. So the speed is constant. Well, that's no surprise. Well, you know, r is constant, omega is constant. We started off with that assumption when we were looking at angular velocity. So the magnitude of the speed is the radius of the circle multiplied by the angular speed. So I'll just indicate the magnitude of this vector. That's v without a line. It's r omega. So if we double the radius, we double the speed. If we double the angular speed, we also double the speed. So v is proportional to both r and omega. Now, in the previous video we saw that the acceleration is given by dv dt, the derivative of vector v with respect to time. And to do that we just differentiate each component with respect to time. So minus r omega is just a constant. We leave that to one side and we differentiate sine omega t with respect to time. The derivative of sine is cos. And we differentiate omega t to get omega. Let's multiply by I. And here we've the constant r omega, and we differentiate cos to get minus sine, and differentiate omega t to get omega. Now we can factorize out minus r omega squared. And then we've cos omega ti plus sine omega t times j. But everything inside here is well, actually I won't take out the r, I'll put the r back in. So now we see that everything inside the square brackets is just vector r. So we see that vector a is minus omega squared times vector r. Now omega is a positive number, it's the angular speed, and that's always positive. So we see that vector a is a negative scalar times vector r. Now if we multiply a negative scalar by a vector, we reverse the direction of the vector. So if we multiply a negative scalar by vector r, we get a vector that's pointing in a direction that's opposite vector r. So vector a is in a direction that's opposite to vector r. So that means that the acceleration of a particle undergoing uniform circular motion is always directed towards the center of the circle. Its direction is always changing, of course, because when the object is here, the direction is now this way, always towards the center, but its magnitude is constant. Its magnitude is given by omega squared times r. If we just get the magnitude, we just write that as a, and we have the magnitude of minus omega squared times vector r. Well, that's just the magnitude of minus omega squared times the magnitude of r. Well, the magnitude of minus omega squared is just omega squared. We just make minus omega squared positive. And the magnitude of r is just written r without a line. So we can see that the magnitude of the acceleration, this is also known as the centripetal acceleration. Centripetal means center-seeking acceleration, is proportional to omega squared and is proportional to the radius.